Alright, let's get into one of the biggest advancements in AI right now, Retrieval-Augmented Generation or RAG. This is the technology that's transforming AI systems from being impressive to being genuinely reliable. So let's break it down. We all know that even powerful language models sometimes produce answers that sound confident but are completely incorrect. These hallucinations happen because an LLM is trained on frozen data. It can't access new information and it has no built in mechanism for verification. RAG directly addresses this. A standard model guesses, a racked model retrieves. It looks up the answer instead of relying on memory, and importantly, it can show you the source behind its response. So here's the flow. We'll look at the limitations of LLMs, introduce RAG, explore the two pipelines, add advanced retrieval techniques, discuss evaluation metrics, and wrap up with practical use cases and troubleshooting. Before RAG, search systems struggled with the semantic gap. Traditional search engines matched words, not meaning. They couldn't connect a query like New York's best pizza with top pizzerias in the Big Apple. This mismatch between wording and intent is exactly what RAG solves by combining semantic search with generative reasoning. So, what is RAG? Think of it as giving an LM an external, continuously updated knowledge base. Instead of relying solely on outdated training data, the model retrieves up to date information and uses it to ground its answer. It becomes an open book system rather than a closed one. Racks through two main pipelines, the indexing pipeline and the retrieval pipeline. In the indexing pipeline, we gather documents from various sources, split them into smaller segments, convert them into embeddings, and store everything in a vector database. Chunking is an important step here. You can use fixed size chunking, semantic chunking that breaks text by meaning, or overlapping windows that capture context across boundaries. The right strategy depends on your use case. Once chunked, these pieces are turned into embeddings, dense vectors that represent meaning. Embeddings create a map where similar concepts sit close together. This is how semantic search becomes possible. These embeddings are stored in a vector database. Common systems include FAISS for local setups, Pinecone, and Weaviate for cloud deployments, and Chroma for lighter applications. They are optimized for fast similarity search using algorithms like HNSW or IVF. Once the knowledge base is ready, the retrieval pipeline handles real-time queries. When a user asks a question, the system embeds the query, retrieves the most relevant chunks, attaches them to the prompt, and sends everything to the LLM with instructions to use only that evidence. The model receives not just a question but curated context. That's grounding. Retrieval itself can be done in several ways. Basic RAG uses k-nearest neighbors on embeddings. More advanced setups use hybrid search, combining BM25 keyword search with vector similarity to improve accuracy. Some systems also use sparse embeddings or weighted scoring to boost performance in domains with heavy terminology. Production grade RAG introduces several enhancements. Re-ranking improves the relevance of retrieved chunks by reordering them using a lightweight model. Query transformation rewrites user queries behind the scenes to make retrieval more accurate. Corrective R or CRAG performs a fast quality check on retrieved content and filters out noise. And source attribution ensures the final answer comes with citations so users can validate the information. Evaluating a RAG system requires actual metrics. Common ones include precision at K, recall at K, and mean reciprocal rank to measure whether the right documents are retrieved. Hallucination rate can be tracked separately by checking how often the model uses content outside the retrieved context. These metrics help teams iterate on chunking, indexing, and retrieval logic. Even with all these, issues can still appear. Missing content is the most common problem. If the answer doesn't exist in the knowledge base, the model can't retrieve it. You may also see irrelevant chunks, poor ranking, or formatting mismatches. But each of these has a solution. Improve chunking, adjust overlap sizes, enrich your data sources, or refine prompts and retrieval rules. RAG is already powering real-world applications, enterprise knowledge search, customer support automation, medical and legal grounding, compliance analysis, financial research, and even coding assistants that rely on accurate documentation retrieval. Anywhere reliability matters, RAG is becoming the default architecture. So the takeaways are simple. RAG reduces hallucinations by grounding an LLM in real, up-to-date information. It works through indexing and retrieval pipelines. Embeddings, chunking strategies, and vector databases are at the heart of the system. Advanced techniques like hybrid search, re-ranking, CRAG, and query rewriting dramatically improve accuracy. And evaluation metrics ensure your system is performing the way it should. RAG represents a major step forward in building AI systems that are not only powerful but dependable. And now that hallucination control is becoming solved, the next frontier is figuring out how to make these systems truly intelligent, not just informed. Thanks for joining me.